Hello, this is how to install and use the software Wireshark on Windows operating system. This is the wiki page. Wireshark is a network analyzer, analyzes TCP, IP, UDP, ICMP packets. This is the website. Let's download. Windows 64-bit installer. This is how it looks like. It also works on other operating systems than Windows, on Linux and Mac OS. Here in the main list you displays the captured packets, and then for the selected packet there's details. The installer finished downloading. Let's see how we install it. It requires Elevate as administrator. It's going to install Windows kernel modules, EULA, these are the components that are part of the installer. Wireshark is a graphical user interface application. T-Shark is text user interface application. You can also gather packets from network interface cards, but also from USB, start menu item, and this is the Windows kernel module, npcap. So pcap is package capture. There used to be another Windows kernel module named WinPcap. It's going to appear in add remove programs. So in add remove programs, we will have two new installed applications, npcap and Wireshark. USB capture. I'm not going to use USB capture, so I'm not going to install USB pcap. The application is 64-bit. The Windows operating system is 64-bit, so the install directory is c:\program space files. This is another installer, the installer for the Windows kernel module npcap. I'm keeping all of the defaults when installing both products, npcap and Wireshark. Next, and finish. Next, finish. So let's look at the list of installed applications. Right-click on the Start menu, Installed Apps. In here we should have the pcap and pcap application and the Wireshark application. In the Windows Start menu, at letter W, at the end of the list, there should be Wireshark graphical user interface application. Let's start it. In here, we should select the network interface card that we want to capture packets from. Let's first look at the list of network interface cards that we have on this computer. I right-click on the system tray network and I go network and internet settings. I'm looking for the old control panel network interface cards setting. Where is that? Control panel, network and internet. Network and sharing center. Okay. Change adapter settings. Finally, I'm where I want it to be. So again, the steps in the Windows Start menu, I search for control panel, wrote control, got to control panel, then network and internet, then network and sharing center, and then change adapter settings. And now I'm at the list of network interface cards. Says that there's just one network interface card. This is a virtual machine. This is the network interface card that we have, virt.io. Let's also look in the device manager. So right click on the start menu, device manager. We're looking for network interface cards in here. At the chapter network adapter, I've expanded it. So it says one mini port, wide area network mini port for various connection protocols, PPOE, etc. So just one network interface card. There's no Wi-Fi, there's no nothing else. No VPNs, no virtualization software, network interface cards. Okay, and the name is Ethernet. Let's go right click on it, properties. Let's see what are the settings. It has TCP IPv6 with DHCP, TCP IPv4 with DHCP. Okay, let's now look at the network interface cards from the command line. So I'm at cmd.exe. Not elevated as an administrator. ipconfig/all. Okay, these are a general category of information about networking and the Windows TCP IP networking stack with WSOC from BSD. And then there's chapters, one chapter per network interface card. So this is for this network interface card named Ethernet. It says Ethernet adapter and then the name of the network interface card, Ethernet. We can see that it uses DHCP. It has received the IPv4 address ending in 254 from the DHCP server, which is the virtualization software, virt manager that runs the Windows virtual machine. The IPv4 address of the virtualization software of the host machine is ending with 1.1 and .254. And the rest of the network interface card IPv4 address is 192.168.122. And there should be a MAC address, which is this one, physical address. Back to Wireshark. And now we know that we want to capture the network interface card Ethernet. So there's this option, adapter for loopback traffic capture. So this is for the IP, for the network interface card loopback device, which is this guy. (127.0.0.1). Let's prove that we can ping the rest of IPv4 addresses. The IPv4 address of the network interface card Ethernet. the IPv4 address of the host operating system. Event tracing for Windows. So this is probably for, I don't know, for reading Windows event logs. I'm not exactly sure what for, but we're going to select Ethernet. So double click on Ethernet and the capture has started. Let's see how the capture works. We can stop the capture. We cannot pause the capture. So let's stop it. We can start the capture from the Wireshark main menu, capture and then start. Continue without saving. And in order to stop it, the application icon has changed. Now it's green in the title bar. And to stop from the Wireshark main menu, capture and then stop. You should aim to have a capture that's as small as possible. So the capture is the information that's shown in the main list view that starts at the moment that you have started the capture and stops at the moment that you have stopped the capture. So now we have a capture. This is the newest event captured with an ID 1643, the order number, and the first captured packet is with ID 1. Okay, within a capture, let's see what's available. So again, this is a list view with all of the captured packets. 1643. You can select each individual packet, like for instance, let's select the packet 15. And then you can find all of the information that's stored inside of a packet. And that information is the timestamp, so either relative to the moment that the capture has started, so the delta between the first packet and the current packet. In this case, it's seconds 0.083. So that's 83 milliseconds from the first packet captured. Or you can display human readable timestamps. That can be configured from the Wireshark main menu, view, and then time display format. The default is seconds since first captured packet, and you could go to whatever is more familiar to people, which is year, month, day, hour, minute, second, and then fractions of a second. Or you could have just the day part removed, so just a time. Let's see this version. Otherwise, the column will be very large if you display also the date, not only the time. Okay, then you have source and destination. Source, in our case, we're only using IPv4. We're not in a IPv6 network. So that's a great advantage. It's easier to not have both IPv4 and IPv6 traffic, only IPv4 in here. And says that the source is .1, which is the host operating system. Let's actually detail a bit this information. So the packet number 15, the timestamp is this one, hour 5, so that's 5 a.m., minute 43, 2 seconds, and this is the fraction of seconds. Then we have source 192.168.122.1 and a certain port, and then destination. Destination is the Windows network interface card Ethernet. So the IPv4 ending with 254. And then says that protocol is TLS v1.2. From the protocol, you probably can guess the TCP port, or if it's TCP or UDP traffic. Let's find out. So it says that there's networking layers, there's network interface card device NPF with this globally unique ID. And then there's the Ethernet protocol on top, which deals with MAC addresses. So the MAC address is 52.54.00F7, this thing, destination, 4F and 6F. And the source is similar because both the destination MAC address and the source MAC address are actually from the virtualization software. So they're made up, and the IPv6 addresses are in the same block, and the MAC addresses are also similar. Like in this case, they start with 52.54.00, and then they are different from the host operating system to the virtual machine. The IPv4 addresses are for the Internet Protocol, so IP. Then on top, we're not using UDP, we're using TCP, and TCP has ports. The source port is different from the destination port. So source port was 41662, and destination port is 3389. Okay. And then on top, there's security. So SSL, TLS v1.2. Okay, let's find out what exactly is this line. What is this packet representing? The best guess that we have is the TCP port. So this port, we can guess that it's randomly generated. So this is probably a TCP client application. Whereas this one, because it's shorter, so this is really long, I guess there is no assigned TCP protocol port for 41,662 TCP port, but I guess that there is a TCP port assigned for 3,389. We're going to search on the internet. So we go wiki TCP port list of TCP and UDP port numbers, Control F, Control V, and says that 3389 is the server for Microsoft's remote desktop protocol. Okay, so Microsoft has a protocol that allows you to connect in graphical user interface mode to a Windows machine. That's called Microsoft Terminal Services, or the protocol is called Remote Desktop Protocol. The software, the server software and client software from Microsoft had different names, different branding names. Okay, so destination means the Windows machine is running a server of type RDP that's listening on the default port 3389. We could also look at the open ports. So that's netstart minus -nobp TCP. We need to be administrator, so let's do that. Windows Start menu, search for CMD, right click, run as administrator, yes. Arrow dock it to the right half of the screen. Don't increase the font size. Okay, netstart minus -nobp TCP. Let's start from network statistics, and the command line says P means protocol, TCP. We don't want to look at the open UDP connections, just TCP, minus all listening, whatever. I have just memorated this command line because I'm using it more than 10 times per year. And I did this thing for more than 20 years. Okay, so let's see what this list says. This list says the port on which a TCP client or server is using. So port 0.0.0.0 for state listening means that at this TCP port 135, a server is listening, and it's listening on all network interface cards of the current Windows OS installation. So both on the network interface card of the local loopback, so that's 127.0.0.1, but also on the network interface card Ethernet that ends in 254. And if you add additional network interface cards to your Windows installation, again, by installing VPN software, by installing virtualization software, by adding, for instance, a USB network interface card, then on all added network interface cards, this process with process ID 1380 will listen. Okay, so listening means TCP servers. And we're interested on what is listening, so what is the TCP server that uses the TCP port 3389. It might listen on port 3389 either on IPv4 address 0.0.0.0, which means on all network interface cards, or just on our Ethernet network interface card, which is the one with TCP IPv4 address ending in 254, like this. So 192.168.122.254, and the state is listening. This is an example. There's a TCP server with process ID PID4 that's listening on port 139 just on this network interface card, not on all network interface cards. Okay, and we could even filter by listening. And now we can look for 3389. So 3389 in here and pair just one network interface card. There's no such thing. So the only process running on the Windows operating system that's listening on port 3389 and is a TCP server is the process with process ID 15676. Right click on the taskbar and select Task Manager. Select the Details tab and then have the process ID column visible. You can eventually put it on the first position. Order by the PID column by clicking once. And then we go to the process ID PID 1576. 1576, this guy. So there's a Windows service that has this IP address and we do not know which one. For that, I'm using sysinternalsuite. It's just a zip file that you download from the Microsoft website. This. I've extracted it. And now I'm searching for the executable procx. This one procexp.exe. I'm doing the same things that I did in the task manager. So sort processes by process ID. Go to the process ID 1576 and hover on top of the row. It will say that this is just one Windows service. Some of the SVC host processes. So SVC means service and host is the host. So there's a special executable that hosts most of the built-in first party from Microsoft Windows services, and it's called SVC host from the place that you would expect, which is /Windows /system32 /svc host.exe. So in this case, for 1380 process ID, the process svc host.exe hosts two Windows services, RPC, remote procedure call, and RPC remote procedure call endpoint mapper. But for the one that we're interested in, which is 1576 process ID, svc host.exe hosts just one Windows service, which is the one which we expect. So the remote desktop protocol server called remote desktop services and short service name term service. Term from the terminal services. Terminal in the sense of a Unix mainframe terminal. VT monitor plus keyboard plus mouse. Okay, so now we know that this captured packet, line 15, is not TLS v1.2 protocol, but it's in fact protocol RDP. And this is the RDP protocol. Default TCP port 3389. There's a server built into the Windows operating system. There's also the server XRDP that works on FreeBSD and on Linux operating systems. Okay, this is all of the packet. So starting with this 52 and ending with this 21. So this is a hex view of the bytes that are part of this capture line 15. Starts with this 52, ends with this 21. Each of these bytes, so this is 1 byte, which means 8 bits, which means 2 hexadecimals. Let's use an application such as Windows Calculator, calc.exe. We switch the mode from this 3 lines button to programmer. We go to hex, we write 52, and then we see that indeed it's a single byte, because we look at the row bin, which means binary, which means base 2, which means a numeric system that has just 2 digits, which is 0 and 1. So 0, 1, 0, 1, and then 0, 0, 1, 0. 8 bits in total, 1 byte. It's easier to read as a human, 52, and to remember 52 than it is to remember 0101, 0010. And why hexadecimal, not decimal? Hexadecimal means that this 5 is actually 16 times 5, not 10 times 5. So this is not 52. This is actually 5 in hexadecimal, the digit 5, and 2 in hexadecimal, the digit 2. The digits in hexadecimal are from 0 through F. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. Whereas in decimal you have from 0 to 9. Okay, so this 52 is just 8 bits, more 8 bits, more 8 bits, more 8 bits, more 8 bits. 8 bits is a byte, a byte, a byte, a byte, a byte. In total, I don't know how many. How can we compute the number of bytes? So 1, 2, 3, 4, 5, 6, 7, 8, 16 times 6. Back to simple. 16 times 6. 96 plus 2, so 98 bytes have been transferred from the host operating system towards the current operating system, the Windows virtual machine. They started from port 41662 and arrived on port 3389. The ports of the TCP server are important to be fixed, because that's how clients know how to connect to a TCP server, by specifying that they want to create a connection towards the Windows machine at TCP port 3389. Whereas the TCP port of the TCP client, in our case, we're using the FreeRDP Linux remote desktop protocol client. This is random. If I disconnect from the Windows machine and reconnect to the Windows machine, this source port will not be 41,662 any longer. It will be something different. Okay, so these are all of the bits and all of the bytes. Bytes represented as 2 hexadecimal digits. And then this is the same bits represented as what? I'm going to guess at as ASCII 7-bit. Okay, so these bits represent an entire packet which has multiple layers. There's the frame, there's Ethernet, there's IP, there's TCP, and there's security. You can see how they come after each other. So the entire frame starts with the bits of the Ethernet protocol. Then they're followed by the IP Internet Protocol bits, then by the TCP protocol bits, and then by the security bits. Security in the sense of maybe the remote desktop protocol can also provide plain text transfer, but this layer, TLS layer, makes sure that a person that's inspecting the bits coming from the RDP client towards the RDP server cannot see what's actually inside the packet, cannot look at the username, at the password that I have specified when I have connected to the RDP server. Cannot see if this is a mouse press, a keyboard press, or if it's notification from the RDP server that the mouse has moved or the cursor has changed, etc. Okay, this is an extremely complicated protocol because it has security on top. We want to look at another protocol that's way simpler, that's plain text, where we can read all of the parts, all of the layers of a packet. For that, I want to use the TCP protocol named HTTP. So not HTTPS, because this is complicated, is all of the packets are, for security reasons, encrypted, whereas the older HTTP without an S protocol doesn't do any encryption. It's all of the bits are plain text, and we can see, for instance, ASCII text in there. Okay, let's prove that this is actually HTTP. So the URL is http:// not https://. Okay. Let's actually inspect the page. Let's go to the network. Where is it? In here. Let's refresh the page by disabling cache. So I have checked the checkbox disable cache, and I'm refreshing the page. I'm using the web browser Mozilla Firefox in a private window. Okay, so let's see. This is the HTTP traffic. Says all file types. So there's a get httpforever.com/. This is the request. So http/1.1, which is the name of the protocol. Then get, which is the HTTP verb. And then the URL containing two parts, the protocol and host. And then the query string. In this case is just /. And as response, we have that gzip compression is possible, that what follows is text HTML, and where is the body? This is how the HTTP client, which is Mozilla Firefox, has requested the page. So get/http1.1 host httpforever.com user agent. This is a string that identifies the type of HTTP client. Says that the HTTP client knows plain text HTML, knows English US, knows compression using gzip and deflate, which is, I know, zlib. Do not track. And it wants no cache because we've selected disable cache. And this is the response body formatted as HTTP. And if we go to raw, we can see the machine readable HTTP content. This is the human readable version of the HTTP content of the body, and this is the machine readable version in HTML format. Okay, and then this page has required other resources, some JavaScript files, a favorite icon, which is this red lock, this thing, CSS for styling, and additional images. Maybe this mountain is an image. And even special fonts for this page. Okay, so we kind of have an idea how the HTTP TCP traffic from Mozilla Firefox towards httpforever.com works, but we still want to see way more in depth this traffic using Wireshark. For this, we want to have Mozilla Firefox ask again for HTTP forever, have a complete traffic. So that means make sure that disable cache is enabled in the inspect queue. We go capture start, continue without saving. So we're not interested in the previous capture. We want a fresh new one. Continue without saving and then refresh in Firefox. and we can see all of the traffic. We're interested in just the first line in here. Let's stop the capture as fast as possible. We're not actually interested in any of the JS or CSS or SVG or font files. We're interested in just the traffic for this one, for slash. So that's why it's important to stop the capture immediately after what you're interested in has been collected inside of the capture. Okay. We can see traffic from the Windows machine towards the host machine, but we're actually interested in traffic towards httpforever.com. Let's see how that works. What is the IP address of httpforever.com? Okay, so it's the one ending with 39. Now we should try to find the first packet that has been sent by Firefox towards HTTP Forever. We have more possibilities. We could sort by protocol and see the protocol named HTTP. The protocols are sorted ascending, so it starts with letter D, DNS, and we want to go at letter H, HTTP, this guy. Then we want to make sure that we're looking at the very first packet in order. So 484 is smaller than any of the other package numbers. This is the one we're interested in. So we go right click on it and go follow TCP stream. And this is how it looks like. There's multiple TCP packets being shown in here. It's all of these TCP packets. We can see that Wireshark has filtered our capture. So we started the capture, we stopped the capture, nothing changes inside of the capture, but we're not viewing the entire capture in Wireshark, we're viewing a view of the capture. So this view of the capture means applying filter tcp.stream equals 1, this thing, to the capture. So again, we're seeing a view of the capture. The view is really short, contains just 30 TCP packets, whereas the entire capture has 3,335 packets. We can go back to the previous filter. So this is the filter combo box, similar to a address bar. Inside the combo box, we could either write text. Let's see if that works. So tcp.stream equals 1. tcp.stream. So this is showing the grammatically valid possibilities. EQ is a operator, binary operator, comparison, equal, and then 1. I'm not sure if equals works. Just equal is invalid grammar. Might be that the operator equal has a slightly different implementation and meaning than the operator EQ, depending on the type of operands. I have traditionally used equals equals, not EQ. Okay, let's close a bit some of the applications running. Wireshark is a graphical user interface application. Right now has two windows. There's the main window, the one with the icon in taskbar, Windows taskbar. And then there's a second window that's showing a follow TCP stream. Again, the main window contains just a filtered view of the capture, whereas this dialog that's not modal, the Wireshark follow TCP stream, is showing ASCII string version of multiple packets, multiple TCP packets. So the first TCP packet is this thing. So it says GET space and then slash and then space. This 20 is the ASCII code for space. Let's look at the ASCII table. So this is the ASCII table. Some operating systems, some protocols respect this table, at least for the first 7 bits. And this is what we're showing here. So it's just 7 bits, which means decimals from 0 to 127. The superior bit out of 8 bits, so the 8th bit of 1 byte, that's not as clear cut as the first 7 bits. But again, many operating systems and protocols actually have very similar values for decimal 0 to 127 when represented as a character from the English alphabet and not only. So we're looking at 20 in the sense of T0, 20 hexadecimal, and that's the character space. We're at this character. Then we want to look at this character, uppercase G, hexadecimal 47. So hexadecimal 47, where is it? No 47, but 47 is uppercase G and decimal 71. The columns for decimal, hexadecimal, and the ASCII character. So G is 47, E is 45, and then T is 54. This guy. Then a space, which is 20. This 20. And then a slash, which is 2F. And then another space, which is 20, uppercase H, which is 48, etc. So there's just bits, but all of the bits starting from G are actually in the ASCII table. And that's what is presented in this Wireshark window. So says, where is it? Get. So GET space slash space HTTP. get space slash space http slash 1.1. Then there's ODOA, which are really important ASCII characters. Let's look for them. So OD is this guy, CR, carriage return, so \R. And the next one is this guy, OA. OA is this one, A hexadecimal, 10 decimal, \n, LF. Let's write this down. So \R, \n is the Windows end of line terminator. It was also used by other operating systems before Windows. That's why when the HTTP protocol was invented by Tim Berners-Lee, \R, \n was chosen instead of the logical \n. DOS, MS-DOS, PC-DOS, etc. have used \R, \n before, and maybe other operating systems. Nowadays, \R, \n means some protocols plus Windows. The rest is \n, which is the Unix, Linux, Mac OS, Android, etc. end of line character. Okay, \R, \n is hexadecimal 13, hexadecimal 10. \n is hexadecimal 10. LF \n and CR \R. Okay, so it uses ODOA \R \n to advance to the next line. So to separate lines, line separator, end of line. End of line, and then it goes host colon H lowercase o st. Some parts of the HTTP protocol are case sensitive, some are not, most are not. Okay, colon, so colon says that we're most probably looking at the HTTP request headers, which we can see in Mozilla Firefox. Where were we? In here. So the this is the response headers, request headers, this thing. Okay. Why? Because colon is specifying a PK pair, a VK pair, a value, a key value pair, whatever. So this is a property, this is the property name, this is the colon that separated the property name and the property value. So a key value pair inside the request headers using the HTTP protocol. Okay, then another new line, which is this guy, 0D0A, and then goes with the user agent. Again, user agent, is used by the HTTP client to tell the HTTP server some hints about what type of HTTP client this one is. Unfortunately, this string has been abused a lot, and many of the HTTP clients have an extremely similar identification string for the user agent. Most of them have Mozilla, most of them have I don't know, 5.0. Even if they're not actually using the original Netscape rendering, HTML rendering engine. Okay. So after that, there's another \r\n in here. And then there's the accept line in the headers. Then the accept language line in the headers. Let's see how the bottom left tree view looks like. So the body of the Wireshak application shows a list view of captured packets. Once you have selected one of the packets, in the lower right pane you can see the hexadecimal view of that packet. So that means base 16, but also best effort trying to convert the half of whatever, converting 7-bit of a byte to a ASCII character using the ASCII table. So using this guy. But then in the bottom left tool window, we can see a tree view that's representing the same bits. So the same bits from 52 to 0A are also represented as this very complicated human readable tree view. Again, the frame is everything, and then Ethernet is just the first bits which are part of the Ethernet protocol. The next bits are the Internet protocol, then follows the bits for the TCP protocol, so not UDP but TCP. And then we can see in here that the destination port is 80, which is the default TCP port where HTTP servers that serve HTTP protocol, not HTTPS protocol, are listening to, so port 80. Whereas the HTTP client, which is Wireshark, uses some random TCP port on its operating system, so 54,280. And then the rest, the bulk of the bits, are for the protocol that's on top, which is HTTP version 1.1 without any security, SSL, TLS, etc. So everything's plain text. Okay, so let's look at GET. If I click on the ASCII representation, it also selects the hexadecimal representation of the word, and it also selects the tree view representation, which says that this GET, all uppercase, is in fact a HTTP verb, so an HTTP request method from the protocol that we're specifying next, so HTTP 1.1. This is the query, the relative path, whatever, the absolute path HTTP that we're requesting, which is / request URI URI uniform resource identifier. The user agent is represented as another line in the tree view under the HTTP protocol. There was a get, there was a host, there was a user agent. So all of the HTTP header key value pairs are represented the way we would expect. We can also see \r\n, the end of line Windows style terminator. Accept language, accept encoding, do not track, GPC connection keep alive, and then two no caches. We could also see that information in Mozilla Firefox in the inspect queue. In the tab network, if we did disable cache and refresh, we can see for this packet the exact same request headers. And then this is followed by this very important \r\n. So there's an empty line. So after no cache, there's a \r\n, but then there's an extra \r\n, which in this case is the end of the transmission. So the end of the packet that's being sent by the HTTP client towards the HTTP server and contains the HTTP request. After that, the HTTP client is done and is waiting for data on the TCP connection from the server. And the server provides a huge package, which is which one? The one that we're using gzip encoding, so we can't really see the body that we have received for HTML protocol. Let's try to rerun the HTTP transmission and see if we can specify no compression. In Firefox settings, whatever, in the Firefox address bar about :config, I search for network.http.accept-encoding. It says that gzip and deflate are the default. I probably can empty this one. I might be able to say identity, so we'll see exactly which one works. Apply. And back to where we were. Disable cache and refresh. Let's refresh the package capture. Capture, start, continue without saving, refresh, capture, stop, sort by protocol. We can see in this scroll bar, the minimap, that the color green is different from the rest of the color. The color for the protocol DNS is this light blue, and this light green is for the protocol HTTP. So it's easier for us to jump straight to the letter H if protocol is sorted. Again, we need to look that the packet number for the first one in HTTP is the smallest possible, 566 it is. That means we can follow it. So right click, follow TCP stream. And now we can see actual ASCII characters instead of a binary gzip. So the difference between what we have now and what we had before is that this part, after these two new lines, the part starting here until here, was not ASCII plain text, is it human readable, but in fact it was compressed as using the gzip protocol. So gzip is a file format. It is used to compress compressible bytes. Okay. This is the HTML view of the body of the page. These are the reply headers. Again, as pairs of keys and value, property name, property value, separated by colon and space. I'm not sure if the space is mandatory in the HTTP protocol. And the reply starts with the protocol, so HTTP and version /1.1, and then 200, which is the HTTP return status, and the human readable version of it, which is okay. 200 is okay. Okay. Inside the body is what we expect, so the HTML page, the source of the page, which you can obtain by going right click on the page and view page source. And inside of the header is metadata about the body, the content of the body, such as it says that the content of the body is HTML, is 5124 bytes long. Okay, some information about the server, a timestamp, when it was last modified 2 years ago, expiration tag, etc. Okay, so that's the traffic for the HTML page, but then the web browser inside of the HTML page, once it starts to understand the body of the HTML page, says that the HTML page is incomplete if this jQuery min.js file is not downloaded from this URL. And also this HTML page is not complete without scale.min.js and init.min.js and scale.min.css, etc. Other CSS files. That's why the TCP communication ends up by not requesting just an HTML file, but also continuing with requesting image files, ICO file, SVG file, WOF file, etc. In here, where the web browser requests via HTTP protocol GET additional files other than the default, which is the path slash. So it requires the path /js/init.min.js. Because this, I'm not sure why it requests with a relative path, why it requests this file and not starts with this one. Okay, so it requires this one, which is a maybe single line. Everything's written in a single file, no spaces, no anything, so it's minified JavaScript. Then it wants a CSS file. That's also single line with a minimal number of spaces. An SVG, which is an XML format, which has a ton of new lines. And the SVG only contains 3 polygons. Okay, this is maybe for the, I know, for the lock icon. Okay, you can close the view on the capture by clicking on this close button. Or by you can just delete the filter yourself. Okay, so you can follow all TCP communication, right click, follow. This is a UDP stream using DNS protocol. Some protocols are less human readable than others, in the sense that there's compression, there's encryption, or most of the protocol is not about transferring strings, human readable ASCII strings, but transferring, structures of bytes or integers. But Wireshark does its best to transform this short number of bits to something very human readable. So DNS query of type A, somewhere it says A, IN, cdnjs.cloudflare.com. Type A means DNS request of type host address. And the response. So it asks what's the IPv4 address, which is A, or ACE means what's the IPv6 address of this hostname, cdnjs.cloudflare.com, and there's just one reply over DNS that says answers. There's not one but 2 IPv4 addresses. One ends with 24.14, the other one ends with 25.14. And then let's look for it asks for the scotthelme.co.uk DNS query, but not for A, but for HTTPS. So A asks, please convert this domain name, or in this case, host name, from human readable format to IPv4. The next one wants to know the default HTTPS server that serves the domain scotthelme.co.uk. And the response is in the next packet, 1544. We can click here in the preview. and we can look at the answer of type DNS query HTTPS. There's, I don't know, 3 different HTTPS servers that use IPv4 and 3 more that use IPv6. Again, Wireshark tries at its best to go from raw bytes towards this presentation as a tree view. Okay, let's see some types of simple, very simple filters. Go back to sort as by packet number. Let's scroll here. There's many protocols. There's TCP. There's TLS v1.2, which is actually the remote desktop protocol. HTTP. QUIC, which is one of the newer faces of the HTTP protocol. So HTTP/2, QUIC, HTTP/3. For a QUIC, it's not even using TCP protocol, it's using UDP. QUIC is a very advanced topic. HTTPS is a very advanced topic. SSH protocol is a very advanced topic. SSL in general is a very advanced topic. If you want to learn Wireshark, you should start by using very, very simple plain text protocols. Use the protocol telnet, use POP3 without any security, HTTP without any security, FTP without any security, and use them for at least 80 hours to gain the knowledge, to figure out how many IPv4 addresses are there, what protocol is using UDP, what is using TCP, how hosts are using, how servers are using TCP ports for listening, how to sort the list view, how to comprehend the view as hexadecimal, as ASCII, as tree view, how to show only the information that we're interested in inside of a capture. So let's see only HTTP traffic. How do we do that? That's TCP dot proto. Nope. Nope. It's IP.proto equals. Nope. I know. Let's start reading the documentation. So the filter is just the name of the protocol. Possible protocols are UDP, in this case shows quick traffic. Could be TCP, is going to show HTTP traffic, but also the RDP traffic. You can say HTTP. As you can see, there's multiple versions for HTTP. Let's see if if quick is HTTP 2 or 3. weak. It's neither. Okay, so if you want just to filter by protocol, look at the values inside the column protocol, and search for that all lowercase. There's a manual from the Wireshark main menu, help, and then user guide. Opens a file that's installed on your computer. In here, we want to look at the filtering. There's a toolbar for that. You can place the documentation on the right half of the screen and Wireshark on the left half of the screen. Rim contains squirrels. Wow. Bookmarks for saved filters. You can clear the filter to go back to the entire capture. You can apply. I don't actually click on the apply button. I just press enter. The combo box with a list of previous filters that we have used. Add a new filter button. I'm not sure what this thing does. I have never used this thing. Okay, back to where we were. Compiled filter output. PPF. Oh. We can filter while capturing. We can filter while viewing. Screenshots from the previous version of Wireshark when it was using the GTK toolkit not Qt framework. So just the name of the protocol will show all of the packets using that protocol. Protocol field names are usually lowercase. Okay, and then you can have really complex strings here in the filter expression. View internals supported protocols. Depending on the way you have installed Wireshark, you can capture different parts of the system. For instance, wireless packets, USB packets, Ethernet packets, etc. And you could also have different protocols understood by Wireshark. So Wireshark will be able to tell if a packet is just TCP or a very specialized form of a TCP protocol. And that will also make the way the tree view is displayed for a selected packet way more complete if you have support for additional protocols. Okay, so when you filter, you use one of these strings. There's 3,000 protocols. Let's see if it knows DNS. Yes, it does. The comparators, the binary operators, there's EQ or equals equals. In here it says that they're equivalent. NE not equal all if more than one. Not sure what that thing is. Greater than, less than, greater or equal, less than or equal, contains. Mhm. Two. Okay, so these are the operators. The way you specify an IPv6 address, IPv4 address is specified the way you would expect. There's CIDR, the IPv6 ranges with slash. There's the string surrounded with double quotes. If any UDP package contains this sequence of bytes anywhere, not just in the MAC address. Let's do that. Let's find the DNS packet. This guy that has FOFD. So it has captured, it has found it. If we're looking at UDP protocol, it did not find it if we're looking at the DNS protocol. Because it's not looking in the entire packet, it's looking inside the, I'm going to guess, inside the bits that are for this protocol inside the packet. So if I'm searching for 7A01, it should not find package 635. 7A01. Where is 7A01? I don't know. Okay, but the bulk of the filters that I have ever used are about seeing what traffic, so the capture will contain a ton of traffic that's totally not interesting to me. It will contain, I don't know, NetBIOS, broadcasts, DNS, requests, a ton of other processes exist on my machine that I'm not interested in, background services, etc. What I'm interested is, for instance, to see all of the traffic to a certain machine that has, I know, an SQL server. And for that, I want to filter all of the packets that go to a certain IPv4 address, all of the packets that come from a certain IPv6 address. And that I have done probably like this. Let's see the HTTP thing. So we're using 30, we have the IPv6 address in here. Let's prepare the filter first. So IP source should be this thing. or IP, I know, destination should be the same thing. Okay, and this should cover all of the HTTP protocol communications. I'm not sure why it's also showing TCP protocol. I know, because it's showing as protocol HTTP only the things that are going towards destination port 80, which is mega bad. Let's fix that. So right click on the protocol column and go. We want to add the two columns for the destination and source port. Column preferences. Add new column. We want IP, we want TCP source, but not resolved. This guy. Okay, and let's see if we can put them there here. Why is it so wide? Okay, so HTTP column, when in the column protocol HTTP is shown, then the destination port is 80. Not really. This is certainly HTTP traffic coming from the server because it contains the body of slash. Okay. Back to where we were, slice operator. What is that? So that's about it. That's the bread and butter. You understanding the network model as best as possible, being able to use the command line, does not matter the operating system, might be Solaris, other Unixes, BSDs, Linux, Windows, macOS, iOS, etc. Hopefully you have access to some command line executables, to some command line tools. There you have something similar to netstat -ano bp.tcp2c on which TCP port a TCP server is listening. Then you have networking troubleshooting tools similar to ping, to trace route, to NS lookup. And then if you have issues, maybe your organization has an issue, networking issue between a custom HTTPS API and an HTTPS client, then what you want to do is to inspect the packets as they are. If Wireshark is not good enough, you might use more complex or specialized tools. For instance, for HTTPS, there's a possibility of making Wireshark be able to view the contents of the HTTPS traffic. There's the possibility of using a self-signed HTTPS certificate. There's the possibility of using HTTPS proxies. There's tools such as Fiddler. But then an alternative is to convince both the TCP server and the TCP client to make the protocol as human readable as possible. As in our case, we told Firefox to not allow gzip traffic, so no compression, the traffic should be just plain text. Then you can, if you have control of the HTTPS server, you might also enable HTTP for development purposes, and you could then monitor with Wireshark the HTTP traffic, not the HTTPS traffic. Or maybe you do a man-in-the-middle attack with replacing the HTTPS certificate on your HTTPS server with a self-signed certificate that you control both the private and public parts of. So this is it. This is how to use Wireshark, a tool that's mandatory for me because I'm a developer. I have used it hundreds of times. It's enlightening what I see in here, and it has allowed me to fix now a various number of issues. This is it. Thank you.